Hello everyone and welcome to We Meet at Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Anticipate EMC with LTSPICE. Our speaker is Sylvain Lebrun. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes left for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and to help us to improve our event. You will receive the link to the presentation in the next few days, and the recording will be available at our website shortly. So now I will hand over to our speaker, and I wish you an exciting presentation.
So, good morning, everyone. Thanks for joining today. We're gonna literally fly over this presentation, which is usually more than 1 hour and a half. But today we only have 30 minutes. So let's begin. I'm Sylvain Lebras, Field Application Engineer for Würth Elektronik France since already 6 years. And let's have a look at what we're going to see today. Next slide. So many of you are already users of LTSPICE. This is what caught your attention, that today we can try to make it EMC accurate to simulate in LTSPICE. So we're going to cover the very, very basics of what you're already doing and show that there is something missing to actually get to the EMC simulation. And we're going to bridge the gap together from going to the functional simulation to the EMC simulation. We're going to see what enables us to make EMC measurement in LTSPICE, what enables us to present the result in the very same way as they are presented when you actually scan a device in an EMC lab. So we're going to go further because it's very convenient in LTSPICE to do algebra that enables you to split things that you actually never see in the real world. So let's begin. We already have a lot of things to do. So unfortunately, we're going to cover only a very few examples because of the time. So next. The first thing is to get the tools ready. When I started this presentation back in 2016, linear technology was still existing. Now it's part of analog device. And you can download now the LTSPICE directly on the analog website. The other tool I'm using in this presentation is RedExpert. RedExpert is the datasheet 2.0 of Würth Elektronik. We're going to see why. So let's start with something you might already know how to do, probably if you started to use LTSPICE. So the good thing with LTSPICE is you pick up any device into the little menu here and go to power device. And once you drop this controller here on the schematic, then you can left click and click on open this macro model test fixture. Once you have a macro model test fixture, you can start simulating already. And this enables you usually to get the output ripple of this buck, so the ripple voltage on this node here, in a few seconds time. But is it accurate, and is it really saving you the outcome mathematics calculation that comes with the output ripple calculation? So when we're talking about outcome mathematics, we're talking about this. So you might already know it. I hope for you. So the voltage equals the resistance multiplied by the current. So there is nothing more complicated to say that the ripple voltage equals the impedance of my capacitor multiplied by the ripple current. So it is a bit more complicated to get these figures, but this is why I'm using RedExpert, because here the RedExpert is providing me with these two information: the impedance of my capacitor at a given frequency, and also once I have inputted the parameters for my DC-DC, it gives me the approximate ripple current. So once I have these two, I can calculate. So next, we're gonna see how to extract EMC accurate data from RedExpert. So really the basics of this presentation is to understand that when we want to be accurate from an EMC point of view, we really have to focus on one thing. It's not the actual value of a capacitor, but it's the parasitics, such as the ESR and the ESL, the parasitic resistance and the parasitic inductance of the capacitor. So in the first region that you see here, we've got the value of a capacitor that makes the impedance go lower with frequency. Then we reach a minimum, which is usually the ESR, and then we see that our capacitor has an impedance which is growing with frequency, and this comes from the ESL. In the EMC simulation and EMC measurement, most of the time we are already working in the parasitic region of our components. So this is why it's very important to have the ESL value and ESR value. We're going to see that the simulation is not always starting with the right values. So here, for example, I use the impedance chart for a given component in RedExpert to get the impedance at 100 megahertz. With this impedance at 100 megahertz, the ZL and the frequency I'm using, I can get the ESL value that I will fit later in my model in LTSPICE. So you've got the details of the calculation. So for example, this big film capacitor has roughly an ESL of 8 nanohenry, and I get this value from the reading on the curve. If we change the technology for the same value, but another technology, here it's a ceramic capacitor, same value, 4.7 micro, then we get a 0.2. That's almost 2 orders of magnitude less than before. So we're going to see that this capacitor is going to give very different results. So let's get back to our simulation, our macro model test fixture that I just opened. So I have the bad news is that our macro model test fixture is unfortunately not exactly accurate. Why? Because it's using a capacitor which has been documented as almost a perfect one. So as you can see here, the ESR is very good, and the ESL is not that it's not filled, it's that it's directly filled with 0 nanohenry. So when it comes to the EMC simulation, this is truly a problem to say that this capacitor has 0 ESL. So here you see we have two things missing here, and we have a 0 which has been put here like it's not the right value. So this is what we had before, and this is what the simulation will look like if we take the actual ESR, ESL, and capacitance value. So if you have a trained high, you can already see a few things. So the trained high will see that here is the capacitance contribution. Here is the change of the voltage of the current direction, and here is the ESL influence. So as you may not be as trained as that, then it's very easy in LTSPICE to split out into individual contribution each and every of this voltage. So here, as I have splitted the ESL, ESR, and capacitor, I can get the individual voltage. So they are given in the same scale here. So you see that at the output of my buck, the ripple comes from various contributions. So here, the charge and discharge of my capacitor makes a 14 millivolt peak-to-peak ripple. Here, the ESR is making a 16 millivolt peak-to-peak. And here, the ESL, at low frequencies, it's making 10 millivolt peak-to-peak. And at high frequency, if we take into account this little spike here, it's making 25 millivolt peak-to-peak. So let's have a look at what it looks like in frequency. So this is the FFT of the individual contribution. So this gives you a very good example of what could actually happen in the output ripple of a buck, in the ripple that you're feeding into a capacitor. So this is very simple with LTSPICE because I take only the voltage and I do the FFT. So as you can see, when the frequency is rising, when we are around 100 megahertz, we see that the ESL value makes a dominant contribution to the EMC disturbances. The ESR on the other end was already a very high contribution to the ripple that we're going to have at the output of this DC-DC. And we see that at the low, with the higher is the frequency, the lower is the contribution of the cap to the ripple. So this gives you a very good example. Many designers, when they have too much ripple at the output of their buck, or when they have too much ripple in many devices, they just increase the capacitance value. So if you're lucky, when you increase the capacitance value, your ESR will go down. But most of the time, as the ESL is rather related to the technology and size of your device, the ESL is going to go higher. So you are getting some better results in the low frequency range, and you are getting worse results in the high frequency range by increasing the size of a capacitor. So today I want that you make an educated guess into picking the right capacitor. So now that I have highlighted the importance of the parasitics, I want to show you. So the first thing is to get the parasitics right to start the EMC measurement. And the second thing is to find the missing link. So I asked this question, what is the missing link between functional simulation and EMC simulation, or between simulation and EMC measurement? Most of the time when you get to the EMC lab, you stare at this thing, which is a spectrum analyzer or an EMI receiver, and you stare at your device and the test. But you forget that this is sitting onto a small device, which is, depending on the situation, called a LISN or an AMN. So LISN stands for Line Impedance Stabilization Network. Basically, it's the combination of two elements. Two low-pass filters that enables you to power your device on the test, and also two high-pass filters. So basically, the high frequency is going through this path. And the low frequency, the supply voltage, is going this way and then back here, because it does not see a lot of impedance because it's low frequency. So what we're doing at the EMC lab is to pick this path, the high pass filter, and to get this voltage here to the EMI receiver. And once we have our EMI receiver, we set a limit. We set a limit line for each and every frequency that we're scanning, and we have a look at what is happening. If we are over the limit, it's not good. If we are under the limit, it's good. So basically, we are just making artificially high impedance in the measurement range to grab the signal that our device is making. So, for example, in the measurement range, the impedance of this low-pass filter is around 50 ohms. So this, it's even more than 50 ohms. The 50 ohms come from these resistors in series. But It means that even with a few milliamps of ripple generated here, you will get a lot of voltage generated here, and you are able to compare it to a threshold, to a limit here. So this is what happens when you make FFT of a buck converter. So here I have added a very simplified model of a line impedance stabilization network. So here is my power supply, here is my low pass filter, and here is my high pass filter, which is taking a fraction of the ripple voltage and analyzing it. So as you can see here, we're already starting to have something that looks like we can have at the EMC lab. So in this video today, we are in the EMC lab, and you're actually sitting on the ground reference plane that was used to make this measurement. So you can see in the back, there is the spectrum analyzer that did this job. And if we compare our simulation together with the measurement, you can see on the screen that, yeah, looks roughly the same. So in green is the simulation, and in blue and yellow, it's the actual measurement. So you see that here we're having mostly the same signal shape, but right now we have only implemented a fraction of what is important in the EMC simulation, because here I remind you the ESL cap breakdown in frequency, we have to model the parasitic and make sure that we have to go to be more accurate. So the difference between our simulation and the reality is that an EMI measurement is the sum of common mode plus differential mode. So the differential mode is quite obvious, and it's mostly 10% of the problems when it comes to EMC. But the common mode is a bit more tricky. And when we are at the EMC lab, we never know, or we very rarely know, what is the contribution of the common mode and the contribution of the differential mode. So to be able to have common mode modeled, we have to make something to our simulation. And we have for that to get into the actual LISN design to understand why is the common mode measured and which way is it going. So this is schematic from a LISN. This is the LISN that we designed for R&D purposes. And this, as you can see, is the assembly of the two low pass filters and the two high pass filters. So the common mode is actually going into the differential mode is actually going this way. So you see when you have a ripple, you have it symmetrically. So here you have the VCC, here you have the GND, and here you have the GRP, the ground reference plane. Sometimes it's tied to the Earth, mostly tied to the Earth. So here, when you have a differential mode contribution, it goes this way. When you have a common mode contribution, it goes the same way, but in a different direction here. And that makes the common mode contribution being able to travel through the ground reference plane. So when you have a look at the LISN design, you see that here we have the VCC, here we have the GND or minus VCC, and here we have the GRP, ground reference plane, which enables the common mode voltage to be measured and to travel back to the source. So right now, we will modify our simulation to implement two symmetrical filters. So here is my LISN for the simulation. It's outputting two different voltages, which are usually not available at the same time in the commercial line impedance stabilization networks. And we're going to see that having these two voltages available at the very same time enables us to make accurate EMC simulation and to understand exactly what is happening. But to enable the common mode voltage to be simulated, we also have to model how it is actually generated. So in a previous presentation, we see that when I'm sitting over the ground reference plane with my LISN, I get common mode contribution from the objects close to the ground reference plane. This comes from the capacitive coupling between the switching node or the device in general and the ground reference plane. And here we also have the coupling of my load, which in this presentation was a phone. So then there is the coupling of the phone case to the ground reference plane. So in our EMC simulation, we have to add these two couplings. So as you can see here, I have removed the direct ground connection from here. So my circuit is floating, and here I got my positive supply, here I got my negative supply, and you see this is now the ground reference plane symbol. So with my ground reference plane symbol, I just have to add the capacitance value here to model the common mode contribution. If you haven't seen the other webinar, what we can show in the webinar is when we are lifting the phone from the ground reference plane, we see that the contribution is decreasing. And when we are making the phone close to the ground reference plane, we see that the contribution is rising. So here, that's the difference between the two curves. So that's the common mode coupling that is arising from this parasitic coupling. So now let's try to do the simulation again, but this time with both differential and common mode contribution. So here it is. There should be an animation starting. Sorry. So this is the reality, and this is now the simulation. So this simulation now has the contribution of the common mode, which is rising over the high frequency. So let's compare them now. So is the simulation fitting the reality? Yeah, rather. So let's do it once again. So we see that here we have a very good correspondence, and in the higher frequency we get almost the same shape. So now we are getting closer, and we have some test fixture that enables us to model both the differential mode interference and the common mode interference. So now, if we want to go further, we have to do one thing, is to discriminate, to split the common mode and the differential mode interference. Here, if we have a look at the differential mode impedance, we see that as it's going alongside the supply lines and going in and out in a symmetrical way, we have 2 times the contribution. So basically, if we're looking at the voltage between the 2 tips of the SMA connectors, or the voltage at the terminals of these 2 resistors, we see that we have twice the differential mode contribution. And on the other end, if we look at the voltage between the 2 tips, we have this time minus the common mode contribution plus the common mode contribution, because common mode contribution is going into an asymmetrical way. So it makes that we have 2 times the differential mode voltage and 0 times the common mode voltage. So it makes 2 times only the differential mode voltage, and we neglect this value. So right now, we can have a look at the symmetrical interference. So the symmetrical interference, when we add the voltages this time, so I take as a reference point my GRP, and I add 2 times the voltages. So I get my differential voltage minus my differential voltage, it makes 0. And now my common mode voltage, I get it 2 times. So this you will have the slides. I already see that there was questions about getting the support in the presentation. You will get all the slides to get back to this. But yeah, you can discriminate, you can split the common mode and differential mode voltage into the simulation very easily. That's something that we do with the FFT. So here, for example, the analyzer 2 comma the analyzer will give you the differential mode, and the analyzer 2 plus the analyzer will give you only the common mode. So you can make this directly into the LTSPICE simulation as soon as you have these two signals available. So to do that, then you click on your time domain simulation, view, FFT, and once in FFT, you just have to read carefully, Alt double click to enter an expression. And as you enter the expression, the analyzer comma the analyzer 2 plus the analyzer, then you can have 2 times the differential mode and 2 times the common mode. You can even cut it in 2 to display it directly. And this gives you this kind of display. And this is kind of magic for many designers to have the split of differential mode and common mode noise. And it really helps you to understand what is the dominant contribution into your EMC trouble. So yeah, EMC is not witchcraft, it's just a science. And now let's make it look like it's real. So the first thing is to adopt the units of the EMC, because by default, LTSPICE is not in the same unit as the EMC measurements. Then we have to load the limit lines. We have to compare and see if we comply to the EMC limits. And then define a frequency range, which is the same as the EMC regulation, 9 kilohertz to 30 megahertz, or 150 kilohertz to 30 megahertz, for example. Or if you're in automotive, you can have several different frequency ranges. So let's have a look here. The default unit of LTSPICE is the volt. So the default unit of FFT in logarithmic amplitude in LTSPICE is the dB volt. And here we have to understand that 1 dB volt equals 120 dB microvolt, which is the typical unit for conducted emissions in EMC. So as soon as we have this, it's just a ratio of 1 million. And as we have 2 times the differential mode and 2 times the common mode, you get it? It's 500,000. So there is one good thing about LTSPICE is if you don't want to input all this calculation, and if you want to modify them outside of LTSPICE, you can have access to the plot settings. So by accessing the plot settings and editing them later into a text editor, you can really make your simulation very, very accurate and looking like a real EMC scan. So here, what I've done is I've made a little program. Let's call it program because it's actually a spreadsheet that opens your plot settings. So this is a plot settings. This is what will be available at the end of the presentation. It's a piece of spreadsheet that enables you to input the frequency, the limit in terms of dB microvolts at the start and the stop, and it will enable you later to paste it directly into the plot setting files of LTSPICE and to draw the limit lines that you can see here, for example. So as soon as you have inputted your data about the EMC limits, then you can display it directly in LTSPICE. But to do that, you have to reload your plot settings. So here, the next thing is defining the frequency range. So typical frequency range is 9 kilohertz to 30 megahertz, but LTSPICE sometimes has a few problems with the 9 kilohertz. So here it's 10 kilohertz to 30 megahertz. And the scale, when it comes to the amplitude, is 0 to 120 dB microvolts. So this is encoded in this statements, And now here is the result. So we have here the limit lines, which are drawn using the lines generated by the spreadsheet. We have our differential mode contribution. The frequency range is from 10 kilohertz to 30 megahertz, so covering a typical frequency range for EMC conducted emissions. And we have both differential and common splitted. So this makes the resolution of EMC situation quite trivial. Here, the first thing I have to do is to deal with the differential mode interference. It's going to be pretty easy once we have this. So what's the best thing? As I told you, the most important here is to care about the parasitics. So let's have a look at the parasitics here, and we see that the ESR is generating a lot of contribution, and the ESL is generating also at high frequency a lot of contribution. So I'm sorry. So here, what we want to do is to reduce the differential mode interference. So the differential mode interference can be reduced using three things: the capacitance value, having a higher capacitance value, having a lower ESR, and having a lower ESL. And there is one technology which is fitting all these criteria. It's the polymer capacitor. The polymer capacitor really enables to solve a lot of EMC problems when it comes to differential mode interference. So this is after adding polymer capacitor, which has both a higher capacitance value and also a very low ESR and a very low ESL. I get all these values from the Red Expert, the same method as demonstrated at the beginning of the presentation. Then the next thing is to do what is the historic job of Würth Elektronik, is to use ferrite to solve the common mode interference problems. So to add a common mode choke into LTSPICE, you have to install the libraries from the website or directly from the library installer that will be available into the downloads. So once you have your CMB series, you can add it at the beginning, at the input of your device. You add your common mode choke. You pick the value you want. So it's a bit tricky. To pick the value you want, you have to use the the right click on the U2, and then triple click on the SPICE model line, and this will give you access to all the different common mode chokes. So here, right click, double left click or triple left click, it's not very reliable, and then pick the right CMC from the list. So this is my EMC situation without the common mode choke, and I had my common mode choke, and yeah, it's pretty nice. I still have to do a little here, but yeah, up to you. So we can see that here we used to lift the common mode. We used to lift the phone from the ground reference plane, so we can also add a common mode choke at the output. But to see the result, then just open the simulation. You will get a lot of surprises. So the next question that often comes with this presentation is: can we separate the common and differential mode in the real life? Yes, we can, and we've been working hard on this subject for about 1 year. And yes, we have the common and differential mode separator that really helps you to separate in the real life the common mode contribution and the differential mode contribution. So it's possible, and there is the schematics, bill of material, and layout which are available at the end of the presentation again in the GitHub. So what's the timing? 35. I guess I don't have time anymore. Let's just see that we can also model mains powered schematics. This is the example of a flyback converter for lighting application. We have to model a few things like the tab parasitic coupling, the transformer leakage inductance that is going to make a very high voltage here when we open the MOSFET, and the interwinding capacitance, which is going to couple this very noisy potential to the output. This is why we usually had a Y capacitor in parallel with the transformer. So here, what we can see is that the differential mode is going through the line and going back into the neutral, and the common mode on the other end is going into another way, which was not expecting at the beginning, for example, in the heatsink of the MOSFET. So how do we calculate and model this? Basically, we have to make the capacitor equations between the heatsink and here the tab of the MOSFET, which is tied to the drain voltage, one of the noisiest into a flyback converter. So we have the area, we have the distance, and we can define the capacitance value. So this is, for example, what happens. This is the voltage which is applied at this capacitor, and this is the current that is seen through this capacitor. And this is a pure common mode interference. So you see that's the voltage which is going through the tab of the MOSFET. So we're running out of time already, so I'm gonna get fast on this. The interwinding capacitance is the parasitic coupling between primary and secondary, for example, in a transformer. And you can model all this information directly into the LTSPICE simulation and see if it fits together with the actual measurement of this device. So there are plenty of examples, but we don't really have time today to cover them all. I know that the brushless converter is kind of a trendy subject these days. So feel free to ask more questions, and we're gonna try to make a longer session about this subject. Thanks for attending, and trust the limitless possibilities of LTSPICE when it comes to EMC simulation. Really, it's a very nice tool, and I look forward to make more simulations with you. So thank you very much. You see, we can even make PFC simulation. So slides and simulation files are available on the GitHub if you want to have access to them. There is updated content there. There is also, because I get a lot of requests, all the LISN and the common mode differential mode separator, which are available also directly on the GitHub. The address might change because now we have a corporate GitHub. So thank you. If you have questions, you've got my email, but allow me a little time to answer there is a lot of people today, and we'll need time to answer. Thanks.
Thank you very much, Silva. It was really interesting for us. So there are a lot of questions, like you already mentioned. We can't answer all of the questions now in a short time. But yes, Silva will answer them later. Maybe just have a look at one question, if this is possible.
Okay.
Silva, will you just choose one?
Yeah, I'm just making the question window bigger because I've got so is your LISN and common mode differential mode separator viable? Not yet. We're working on it. Are there any white papers? Yes, there are white papers. We are currently writing them. They would be released very soon. There was no time, but could you explain a bit the topic of the BLDC driver? It takes more time than I have for the whole question session. So yeah, if we I see that the attendee, if there is question about the BLDC driver simulation, yeah, I see that there is several questions about the BLDC, so we can get back to the BLDC. Okay, so the BLDC, can you see my screen? Is it shared?
No, it's not, but we can change this.
Okay.
A second.
Show my screen number 2. So back to the BLDC presentation. So the BLDC presentation is a bit more complicated. So the first thing you can see is that I'm using a lot of parameters to step through different rise time and fall times and driving frequency. The other thing which is quite complicated is to model the parasitic coupling of the inductor of the windings to the stator, because we see that there is a lot of contribution here, not only for from the differential ripple that we see on the voltage V bus P, V bus N, but also from a common mode. So the common mode is going most of the time from the I dV over dt voltages here and into the stator, using a parasitic coupling here, which is modeled as C10. So basically, it's the capacitance value that is building up between the wire and the stator, and that enables the very high frequency created by the rise time to go through the stator and here to create common mode interference. So there is a lot to say, and there is a lot of different ways to model the BLDC. But here, really, we can see that we have voltage spikes which can contribute to the. So the BLDC driver will be available for download if you want to go further also. So here it's also a way to show that we can use a lot of parameters to have the simulation automated and to find the sweet spot for the operation of the device. And here you can see we've got differential and commode, including into the low frequency range, the kind of typical thing that we get in EMC brushless design, BLDC design.
Okay, thank you, Silva, for getting a few insights. I think we will stop now here, and the other questions will be answered via email afterwards. So thank you very much for your attention, and I hope you enjoyed the presentation. The next presentation topic is thermal characteristics of high current inductors in a GaN-based point of load converter. And the presentation starts at 11. So hopefully see you there and enjoy the digital days, and yes, goodbye.